Welcome to lecture 3 under earth pressure theories. In the previous lecture, we understood active and passive earth pressures and discussed about Rankine's earth pressure theory, and then we also discussed about different assumptions which are involved. In this lecture, we will try to extend what we learned with the special cases for computing earth pressures and with some example problems, and extension of Rankine's theory for a special cases like wall with a inclined face and the backfill soil which is not horizontal, which is having a certain inclination with the horizontal. So, in the previous lecture, we saw the development of these slip lines within the zone of plastic equilibrium through a demonstration experiment which is carried out at IIT Bombay, which is with a retaining wall which is nothing but a cantilever wall which is having a sand as a backfill. So, you can see the sand in dry state having a relative density about 55%, which is constructed by polluating, that is air polluation of the sand, like the way it happens in the deposit happens in the field. And this is the passive side, because the wall movements are not adequate. So, the passive state of plastic equilibrium was not observed here, but you can see here the active state with a movement or rotation about the at the top portion. You can see that different series of rupture planes, which is actually shows the evidence of what actually we are discussing in these lectures. Now, we try to derive a universal equation for determining these earth pressures at different depths, and this can be extended to say for a homogeneous soils having cohesionless soils or cohesive soils, or soils with combination of C and phi in different states, either drained or undrained conditions. So, in this slide we are going to discuss about the relationship between sigma 1 and sigma 3. Sigma 1 is major principal stress, sigma 3 is minor principal stress, and when soil reaches a state of plastic equilibrium can be derived from the Mohr circle below. So, a tau sigma plot is shown here, and which is phi is the friction angle, sigma 3 is the minor principal stress, sigma 1 is major principal stress, and if this intercept is indicated by say cohesion and phi is the friction angle, and we can write from the geometry of the circle, we can write that sin phi is equal to this particular diagram, we can write sin phi is equal to of sigma 1 minus sigma 3 divided by of sigma 1 plus sigma 3 plus 2c cot phi, and this deliberation you would already discussed while learning about shear strength. So, by rearranging these terms here, this we can write as sigma 3 into 1 plus sin phi is equal to sigma 1 into 1 minus sin phi minus 2c cos phi. So, this further simplification and rearranging the terms, we can write sigma 3 is equal to sigma 1 into 1 minus sin phi by 1 plus sin phi minus 2c cos phi by 1 plus sin phi. So, this now changes to 1 minus sin phi by 1 plus sin phi, this term we can recognize now already, which is nothing but a Ka. So, sigma 3 is equal to sigma 1 into 1 minus sin phi by 1 plus sin phi minus 2c cos phi by 1 plus sin phi. This we can write sigma 3 is equal to sigma 1 into 1 minus sin phi by 1 plus sin phi into minus 2c into 1 minus sin phi by 1 plus sin phi. That is by using the trigonometry principle we have written this. So, now substituting for say in the active state of plastic equilibrium, say if this equation to be is valid, then we can say that sigma 3 being the minor principal stress in active state of plastic equilibrium, the active earth pressure being minor, sigma 3 becomes sigma A, sigma 1 becomes sigma V, which is actually nothing but a major in case of a active state of plastic equilibrium. So, with this what we get is that sigma A is equal to gamma z Ka minus 2c root Ka. So, this is an equation for active case with sigma 3 is equal to sigma A and sigma 1 is equal to sigma V for a active state of plastic equilibrium condition. So, now with this equation now helps us say for example a sandy soil like the physical modeling experiment where we have seen in a dry state when the cohesion is equal to 0 then in that case that pressure equation is nothing but sigma A is equal to Ka gamma z. At z is equal to 0 as pressure is 0, at z is equal to h that pressure is Ka gamma h, then the total active earth pressure thrust is half Ka gamma h square acting at a distance h by 3 from the base. Now in this case suppose if you are having a soil, then if you substitute at z is equal to soil which is predominantly say cohesive soil, then with say at phi is equal to 0, suppose if you are having a soil which is predominantly cohesive soil, then you can see that sigma A is equal to minus 2c, that is there is a possibility that the soil actually is under tension behind a retaining wall. So when the soil attains its tensile stress, ultimate tensile stress, it cracks and it actually develops tensile cracks. That is the reason why like some of the retaining walls having say cohesive backfills, the top portions are subjected to tension cracks. So this particular equation now if you wanted to generalize for cohesive soils or soils having both cohesion and friction angle, then we can write sigma z is equal to gamma z Ka minus 2c root Ka, and by using the same concepts like with that when you say for passive state also, when we wanted to derive the relationship between sigma p and sigma v and sigma cohesion and Kp, with that we can arrive the condition for equation for passive case also. In this case the only difference is that the sigma 3 becomes the major principal stress and sigma 1 becomes the minor principal stress, which is nothing but sigma v in passive state of plastic equilibrium. So with this now the generalized equations without any surcharge, if without any surcharge on the backfill surface if you consider, then these are the generalized equations of for computing that pressure. Then sigma A is equal to gamma z Ka minus 2c root Ka, this is the active state, and sigma p is equal to gamma z Kp plus 2c root Kp, that is for the passive state. So follow the same steps as cohesionless soils, only difference is that C dash is not equal to 0. So if you look into it, sigma A is equal to gamma z Ka minus 2c root Ka and sigma p is equal to gamma z Kp plus 2c root Kp. So this is for the passive case and this is for the active case. Now Rankine's lateral pressure diagram for a cohesive soil. So if you look into it here, what we saw is active case with minus 2c root Ka is the earth pressure at top, because Ka gamma z minus 2c root Ka, z is equal to 0, the pressure is minus 2c root Ka here. In case of a passive case, we have 2c root Kp plus Kp sigma v. So this is that equation what we discussed just now, and this total length is distance is Ka sigma v dash. So if you analyze further, now we have a lateral pressure diagram for a cohesive soil which we just now have seen. Once again we look into it. If you look into it here, at certain depth z naught, the negative pressure changes to positive pressure. So it indicates that for soil there is a certain depth, it actually remains unsupported, particularly cohesive soils. So that particular depth is called the critical height. So beyond which the soil can not remain unsupported, particularly cohesive soils. So here that is because there will be a negative pressure and positive pressure which actually gets cancelled, and then the soil will be in equilibrium, and then we can say that it is called safe unsupported height. So this is generally about for a certain type of soils having cohesive strength, then or some apparent cohesion up to 4 to 5 meters. So this is a case where with the passive case, the equation which is now shown in a diagrammatic way. Now just now we discussed about the cohesive soil and critical height. So, if you look into it, this is the equation what we derived, sigma A is equal to gamma z Ka minus 2c root Ka. So, z is the depth at z is equal to 0 here, top of the wall, and where the backfill surface is horizontal, h is the height of the wall, and wall is smooth, that is the Rankine's wall. Now, at z is equal to 0, sigma A is equal to minus 2c root Ka. So, this being 0, it gets cancelled, sigma A is equal to minus 2c root Ka, and z is equal to h, it is Ka gamma h minus 2c root Ka. So, which is nothing but earth pressure at the base. At z is equal to z naught, that is sigma A is equal to 0, that is this point here, then that z naught is nothing but the depth, that is 2c gamma root over Ka. So, this particular depth is also referred as depth of the tension crack. So, moment the soil cracks, then after attaining its ultimate tensile strength, then that depth at, so we can even with this expression we can even determine the possible depth of a tension crack at a particular site. So, z naught is equal to 2c by gamma root Ka with the negative pressure which is shown here and positive pressure shown. So, 2 z naught, which is nothing but the safe that is the critical height of a slope that can actually remain unsupported because of the negative lateral pressure and positive lateral pressure. So, with that we can say that Zc is equal to 2 z naught is equal to 4c by gamma root Ka, which is nothing but 4c by gamma tan into 45 plus 5 by 2. Suppose if this soil is say having undrained cohesion, say friction angle is equal to 0, in such situations the critical height of a particular vertical cut can be determined as Hc is equal to Zc is equal to 4cu by gamma, where cu is equal to undrained cohesion and gamma is the unit weight of the soil. So, in case soil is having both c and phi, then the critical height can be determined by using expression 4c by gamma tan 45 plus 5 by 2. So, in this particular slide what we saw, the possible earth pressure distribution what we get when we have a cohesive soil, purely cohesive soil having with cohesion predominantly and then certain friction angle, then we can say that by using this equation we try to derive the depth of the tension crack, and that we said as a 2c by gamma root Ka, and critical height, that is the height to which actually remains unsupported, that is 4c by gamma root Ka, which is actually given by expression 4c by gamma into tan 45 plus 5 by 2. Now, Rankine's lateral pressure diagram with uniform surcharge. If you look into it here, suppose if you are having a soil, say having gamma unit weight gamma and no water table, and then if surcharge is Q. So, this is possible when you are having a pavement behind a retaining wall or any other utility which is behind a retaining wall, then that actually exerts a unit surcharge on the wall. And how this surcharge can create a surface stress in this surface stress can be transferred as an earth pressure to the soil. That is actually we are now trying to discuss in this slide through a form of a special case where h is the height of the wall, which is again a Rankine wall. At top of the wall the pressure is 0, at bottom it is Ka gamma h. So, now when we have surcharge at the top, then sigma A is equal to gamma z Ka minus 2c root Ka, and Kaq has to be utilized. So, where Ka is the coefficient of earth pressure in active case, which is actually has to be multiplied by Q. So, with that what we add is that if you can see a parallel line to the surface. So, this is nothing but entire Q which is actually transferred in the form of a with the Ka. So, that is actually given here as Kaq. So, at z is equal to 0, the earth pressure diagram for in case with surcharge, then this is with surcharge it becomes Kaq, and then at the top of the wall and at the bottom it is at the that is at a depth z is equal to h, it is Ka gamma h plus Kaq. Say if in sometimes we also have completely submerged soil behind the retaining wall or partially submerged soil. So, in such situation how the earth pressure will change. For example, if you have got a wall which is having a sandy soil or a granular soil, and say water table is there on both the sides and the level is same, then the earth pressure gets the lateral pressure due to water will get cancelled. But if there is say due to some tidal fluctuations, if there is a water which actually can cause a differential water pressure, which is actually required to be considered in waterfront structures, basically in the berthing structures. So, Rankine's lateral pressure diagram with partially submerged soil can be discussed. Consider again a cross section of a retaining wall having height h, and in this case what we see is a water table location at a depth ZW from the ground surface. Here the ground surface which is horizontal, and this is h dash is equal to h minus hw. H is the total height of the wall, and now at by using the equation that is sigma A is equal to, all these examples what we are discussing is for active state. The similar concepts can be used for passive case also, but the Rankine's lateral pressure diagram for partially submerged soil for active state. So, here we will be using a coefficient of active earth pressure. So, here at Z is equal to 0, earth pressure is 0, and at Z is equal to HW at this point, then you can see that the earth pressure ordinate here is Ka gamma HW. So, Ka gamma HW which actually gets transferred here. Now, below this the soil is completely saturated and having say gamma is equal to gamma dash, gamma is equal to here gamma which is equal to gamma sat, if you can say, then Ka gamma dash H is the lateral earth pressure here, and gamma WH dash is nothing but a water pressure which is actually exerted by a water of height H minus HW which is nothing but H dash. So, here the total the earth pressure is now Ka gamma H plus gamma W H dash. Suppose if there is this water table is actually up to the top surface, then what will happen is that then the water pressure which is the earth pressure diagram which looks like this thing, Ka gamma dash H which is actually at the till bottom, and then having a water pressure which is gamma W H. So, presence of the water behind a retaining wall actually causes lateral pressure. That is the reason why for designing or constructing retaining walls, we generally use the drainable fills. That is, in case if the soil is having inadequate say drainage facility, the drainage facilities have to be provided so that the building up of the water pressure behind the wall can be prevented, because designing a wall for the additional water pressure is for conventional walls is difficult. But in such situations where there is a possibility of the tidal fluctuations and then possibility of then differential water pressure is required to be considered. But in this case if so this situation can be prevented by providing adequate drainage provisions so that the water pressure remains 0. Otherwise, if it is required, it has to be if the water pressure prevails, then this is how we have to consider in computing earth pressures. Now, let us consider extend the special case, because we all know that the soil is not an homogeneous, but we can extend this Rankine's theory for computing the stratified even for earth pressures for the stratified soil deposits. Suppose if you are constructing a retaining wall and assuming that Rankine's conditions are they prevail, then in that case we can extend this theory for determining this earth pressure diagrams. So, once we obtain this earth pressure diagram, then that can be extended for designing a retaining wall at a particular site. So, here by using the same concept, the equation sigma A is equal to gamma Z Ka minus 2C root Ka plus Kaq, where here the surcharge is not there. So, if the surcharge is there, for example a highway embankment where which is one of the sites is being retained by a wall, and if it is constructed with different soils, then and if it is subjected to a surcharge, then that surcharge has to be considered. But in this case Q is being 0, so this particular term vanishes. So, at Z is equal to 0, earth pressure is 0. So, this is the starting point of the pressure diagram. This all case actually we are assuming that wall yields about rotates about a toe, and it actually yielded sufficiently to actually produce a active state of plastic equilibrium condition. So at Z is equal to H1 just above AA. So this is, let us assume that in this stratified deposit example we have got say C is equal to 0 and phi 1 dash and gamma 1 and phi 2 dash gamma 2, phi 2 dash gamma 3. So 3 soils which are considered having thicknesses H1 and H2 and H3. H is equal to H1 plus H2 plus H3, and A is the interface between these two soils, that is phi 1 and phi 2 soils, and B is interface between phi 2 and phi 3 soils, and phi 1 is greater than phi 2 is greater than phi 3, and in this case if Z is equal to H1 above AA, so we can see above AA, that means that this particular portion, then actually it is governed by the soil properties which are in this particular region, that is phi 1 dash and gamma 1. So here sigma A is equal to Ka1 gamma 1 H1. So observe that the coefficient of earth pressure, which is actually Ka1, which is actually obtained from the friction angle phi 1. So Ka1 is equal to 1 minus sin phi 1 by 1 plus sin phi 1. So with that, this gamma 1 is the unit weight of the soil in the H1 region. Now the earth pressure ordinate just below AA, that means that we just got this particular point, say now we wanted to get this point just below this thing. Now just below AA the soil is now same height, but the soil is just having a properties which is phi 2 soil, and which yields Ka2 is equal to 1 minus sin phi 2 by 1 plus sin phi 2. So with that sigma A is equal to Ka2 gamma 1 H1. This gamma 1 H1 is now for one simple methodology which one should understand here is that for computing earth pressures, just consider this the top soil, you consider that as a surcharge which is lying. Suppose if I assume that my retaining wall starts from here, now in this case you can observe at depth, say at this level AA, you can see how will you calculate. Suppose gamma 1 H1 is the say surcharge which is acting on this particular level, then we calculate that sigma A is equal to Ka2 gamma H1. So just consider that as a topsoil, you consider that as a surcharge, and then transfer that to as a lateral pressure. So here at Z is equal to H1 above AA, we said that ordinate is here, and Z is equal to H1 just below AA, which is Ka2 gamma 1 H1. At depth Z1 H1 plus H2, that is Z is equal to H1 plus H2, that is at level B, and just above BB. So in this case sigma A is equal to Ka2 gamma 1 H1 plus gamma 2 H2. Now at depth Z is equal to H1 plus H2 just below BB, that is this particular portion. Then now the third soil, which is now phi 3 soil, which is Ka3, which is obtained by 1 minus sin phi 3 by 1 plus sin phi 3, which is actually sigma A is equal to Ka3 into gamma 1 H1 plus gamma 2 H2. Now at above CC, if Z is equal to H1 plus H2 plus H3 is there, then sigma A is equal to Ka3 into gamma 1 H1 plus gamma 2 H2 plus gamma 3 H3. Suppose if the soil is also having cohesion, then we can use the same concept of example, where using this equation sigma A is equal to Ka gamma Z minus 2C rate Ka plus to Ka Q, which we can determine the earth pressures in a stratified soil deposit also. So this identical approach for the C5 soil also can be adopted for with the different stratified C5 soil with in a stratified soil deposits we can use for computing earth pressures. So here what we need to consider is that here at just above AA and just below BB, you try to get these ordinates. So when you try to obtain the resultant pressure, and that is actually gives the resultant earth pressure. That means the resultant of all these this particular shape seesaw type this which is obtained saw type diagram, and that is nothing but earth pressure diagram in case of a stratified soil. This ordinate movement this side and that side depends upon the properties of the soil. If the phi 1 is less than phi 2 is more, so based on that it changes. So with that we can obtain a earth pressure diagram, and by obtaining a resultant we can actually calculate the active thrust. In case if you are determining for the passive case, then we can determine the total passive thrust. So the variation of active and passive lateral earth pressures with depth which are shown here. So in this case we are having a soil vertical wall which is actually soil which is having a water up to the top surface, and now as we discuss in this case this is the earth pressure diagram. the equation of this particular line is Ka gamma dash z. At z is equal to 0, that lateral earth pressure is 0. At z is equal to h, the lateral earth pressure is say z is equal to h naught. In this diagram, h is indicated by h naught. Say Ka gamma dash h naught. So Pa is nothing but half Ka gamma dash h naught square, that is the lateral earth pressure, plus this has got an additional component which is nothing but if the water is there up to this level, then that actually acts as a hydrostatic pressure which is half gamma W. For this case, if the water is up to this level, it acts like a half gamma W h naught square. But if the water table is there on the both sides of this thing case, then what will happen is that the wall, say the wall is submerged, say this part here on the left hand side of the wall there is a water and right hand side of this wall there is a water, then in that case that hydrostatic pressure gets cancelled. Then what the effect of water we need to consider by calculating the submerged weight of the soil and then pressure due to lateral pressure due to the submerged soil mass. Similarly, if you look into here in this, if that condition prevails here and the wall moves towards the fill, then this is the equation Kp gamma dash z and for the pressure diagram, and Kp gamma dash h naught is the ordinate at the base. Then Pp is equal to half Kp gamma dash h naught square is the passive earth pressure thrust. So if you look into it, Kp is greater than Ka, and with that what will happen is that the earth pressure thrust in passive case is much more than in the case of a passive case. So that in case if you are having a partially submerged soil state, then you have got this hydrostatic pressure, or if the water table is there on one side only, then actually it exerts hydrostatic pressure, that is to be considered. And if the wall is actually the surface stress is there, this is how the surface stress is considered laterally. So if Qs is the surface stress which is actually acting, then Ka Qs into h naught which is actually here gets transferred, and Ka Qs h naught is the resultant thrust due to surface stress acting at a certain point. If suppose if you have got a different complicated lateral stresses that need to be considered in the subsequent design. So basically in this slide, variation of the active and passive lateral pressures which are shown, and by knowing this we can actually obtain this equation of this particular line and then earth pressure diagrams. So the once you obtain that pressure diagrams, then you can calculate the active thrust and then passive thrust, and then by considering the equilibrium conditions we can actually design the wall for equilibrium. Now let us consider some examples with whatever we have discussed just now. In the example 1, let us consider for a smooth and vertical retaining wall of height 8 meters. We need to calculate the total active lateral force. So active lateral force, that means that wall moves away from the soil, and its location from the base from the following cases. The soil is basically a fine sand having friction angle is equal to 40 degrees, void ratio 80.85, and the specific gravity of the solids is 2.65 and no groundwater table anywhere. And for the same soil with the same backfill but with the groundwater table rising up to the ground surface. And for the same soil with the same void ratio considering the capillarity. So we have the 3 different conditions. Then we will see that how the influence of suppose if the groundwater table rises behind a retaining well, what will happen to the active earth pressure. So that will actually will tell us the influence of the rising groundwater table on the lateral earth pressure magnitude. So in this case, the case A, if you look into it, 8 meter wall, say smooth wall, Rankine's wall, and the earth pressure diagram is now is Ka gamma h. So using sigma A is equal to gamma z Ka minus 2c root Ka plus Ka q is equal to 0. So q, that is because q being 0, and where c is equal to 0, with that Ka is equal to 1 minus sin phi dash by 1 plus sin phi dash, with that we will get coefficient of active earth pressure 0.2174, and by for the unit weight of the soil which is obtained from the given parameters 14.3 kN per meter cube. So vertical stress is about 114.6 kilonewton per meter square. So at a depth 8 meters the vertical stress is this much, at a depth here is 0. So sigma A is equal to at depth z is equal to 8 meters being soil being uniform, which is Ka sigma V dash, which is equal to 24.91 kilonewton per meter square. So these retaining walls are generally considered as perimeter walls. The active earth pressure thrust units are kilonewton per meter. Suppose if the wall say of about 5 meters length, then total earth pressure thrust acting on the wall in active case can be calculated for the given length. So, but generally these are considered as a perimeter length walls being a continuous and then being a plane strain structures, we get the finally the thrust in perimeter length. So, here in this case please note PA is equal to 99.65 kilonewton per meter and it is acting at a h by 3 from the base, that is 2.67 meters. Similarly, the case B, now the water surface is at the ground, that is at the ground surface here, you can see at the top of the wall. So, this is Ka gamma dash H now being because of the submerged unit weight, which you actually obtained by using this deliberation. Then we calculate water pressure. Now, you can see that tremendous amount of water pressure which actually acts on the wall. So, as it actually rises from the bottom, so actually induces instability to the wall if it is not designed, if it is not drained properly. So, now the net pressure is now 382.0, that is about 3 to 4 times there is a increase in the lateral active thrust on the wall with an raising water table. So, the effect of the groundwater surface on the active thrust can be noted here. So, a case where suppose you have got a soil and then which is actually prone for say capillarity saturation. Let us assume that we have got a complete the saturation is possible in this particular zone, entire capillary fringes develop here. So, this is 3 meters is that zone and 5 meters is which is saturated with water, this is the groundwater surface. Then in this case here that pressure is the total stress is here and then pore water pressure for this case is pore water pressure which is minus 3 gamma W, because gamma W is say 10 minus 30 kg per meter square and 50 kg per meter square. So, this is the raising water table above, this is because of the capillarity nature. So, the effective stress is sigma dash is equal to sigma minus u, with that we will get this particular distribution for the effective stress. So, this is the stress distribution diagram for the total stress and pore water and effective stress. So, this is the vertical stress. Now, that one if you convert into for the calculating the lateral thrust, that is now Ka into 29.43, because Ka which is actually obtained from that for the soil, and now this particular portion of the water induces the hydrostatic pressure on the wall. So, that is gamma W H, that H is equal to 5 meters. So, with that what will happen is that the PA is now 279.81 kg per meter. That is this particular situation is that at pressure diagram changes, and which is actually having Ka into 29.43 at the top and Ka into 151.136 ordinate at the bottom, and the resultant of this trapezium actually is nothing but the total active thrust, which for example which is given here a simplified way, Pa is equal to 279.81 kg per meter at acting at a 2.47 meters from the base. So, the location of the resultant with respect to the bottom can be calculated by individual CG. For example, the CG of this particular portion or rectangle located here at h by 2 from the base, and this particular portion is located h by 3 from the bottom, and then we can calculate, and then CG of this particular water pressure diagram, the combined we will be able to get the total active thrust and then acting at a location 2.47 meters from the base. So, in this example what we saw first is that a case where the dry soil and then raising groundwater table and a soil subjected to capillary saturation. So, these conditions actually affect the active at pressure and then can induce lateral pressure on the soil. So, that is the reason why we generally use drainable or granular soils as a backfill material. So that, and in case the situation is that you are prone to use low quality fills, then adequate measures have to be taken to drain the water behind the wall. The second example, a retaining wall with a smooth vertical back is 10 meters, retains a 2-layer sand backfill with the following properties. So, assume that you have got 0 to 5 meters, there is C dash is equal to 0, phi dash is equal to 30, gamma is 18 km cube. Below 5 meters, that is the wall is total 10 meters. So, below 5 meters the C dash is equal to 0, phi dash is equal to 34. So, 2 soils are there now with the gamma is equal to 20 km cube. So, basically we need to show the active earth pressure distribution, assuming that the water table is well below the base of the wall, and here we have a clear 2 types of soils, and up to 5 meters, and below 5 meters there is another type of soil. So, this particular case is illustrated here. So, C dash is equal to 0, phi dash is equal to 30 days, Ka1 is obtained 0.33 from 30 degrees friction angle, 1 minus sin 30 by 1 plus sin 30. So, 1 minus sin 34 by 1 plus sin 34, that is for Ka2, which is 0.283. Now, by using sigma A is equal to K gamma Z minus 2C root Ka plus Ka that is the universal equation for determining earth pressure distribution for the active case. So, active pressure distribution for the upper layer at Z is equal to 0, that is at this point sigma V is equal to 0, so lateral pressure is equal to 0. At Z is equal to 5 meters, just above this point, then we need to use this soil properties, that is Ka1 0.33 into this 90 km square, which actually is 30 km squared, which actually yields this ordinate. One at Z is equal to 5 meters, but just below this line, which actually is governed by Ka2, that is phi is equal to 30, phi is equal to phi dash is equal to 34 degrees, which is Ka2 is equal to 0.283, which yields now Ka2 into sigma V, that is same vertical stress, but with a different soil properties. With that, what will happen is that this ordinate we computed now at Z is equal to 5 meters, just below this line, which is 25.47 km square. Now, at Z is equal to 10 meters, now we have vertical stress plus the 90 km square plus 20 into 5. So, this 20 is that unit weight. Now, please note that unit weight has also changed here. So, with that 190, now is entire this is governed by, is like a something like a surcharge on this level, where Ka2, which is nothing but 0.283 into 190, which actually yields 53.77, that is the ordinate. So, the resultant of this actually gives the total active thrust exerted on this particular type of 10 meter wall. So, that is how we use this whatever we have learned to determine this earth pressure distribution, and then active earth pressure at rest thrust on the wall can be determined. So, third example, where retaining wall 6 meter high with a smooth vertical back, say is in this case is we should be able to tell a wall pushed against a soil mass, where actually this wall is actually moved towards the soil, and C dash is equal to 40 km square and phi dash is equal to 15 degrees, and gamma is 19.40 kg per meter cube. And what is the total Rankine pressure if the horizontal soil surface carries a uniform load of 50 kg per meter square? There is a surcharge which is acting on the top. What is the point of application of the resultant thrust? This is the problem under question. What we can do is that surcharge is 50 kg per meter square, wall is height of 6 meters, Rankine case, but wall moves towards the backfill, so it indicates the passive case. Now, sigma P is equal to Kp gamma Z plus Kp Q plus 2C root Kp. So, with that what will happen is that Kp for a given friction angle, we can obtain at Z is equal to 0, sigma P is equal to 1.698 into 50 plus 2 into 40 into root over 1.698, which actually will yields 188.9 kg per meter square. That is at Z is equal to 0, because this is a passive case, wall moves towards the backfill. So, 1.698 into 50, that is surcharge at this particular point, and plus this particular portion is due to plus 2C root Kp, that is actually this portion here. At Z is equal to 6 meters, we get Kpq plus 2C root Kp plus Kp gamma dash, that is actually this particular portion at Z is equal to H, which actually is the pressure here. So, at sigma P is equal to 1.698 into 19 into 6 plus 84.9 plus 104 yields 382.54 kilonewton per meter square. So, total passive earth pressure is this much kilonewton per meter acting at 2.66 meters from the base. So, that is how we actually use for active case as well as passive case to determine the active thrust or passive thrust. Now, this particular cases of Rankine theory, all we discuss is for can be extended for a special cases like when you have got a backfill but vertical wall. Initially, let us consider that wall surface is vertical, but it is smooth, and in such situations we can actually extend this theory for calculating earth pressures. So in this particular slide, what you are seeing a Rankine's theory for a extension of the Rankine theory for a sloping soil surface with a smooth vertical retaining wall. So this particular surface, the wall is initially is at this particular position, and when the wall moves away from the backfill, when the wall movement is this side, then is an active case. So here that fill inclination with the horizontal is beta, that is actually shown here, and which is having a soil which is shown in this element. So here in this case, the passive case, the elements are now you can one thing which is to be remembered, noted here is that the surface is not horizontal. In the previous case, we have actually assumed that typical ideal Rankine wall having a smooth interface and as well as backfill surface is horizontal, but in this case you have got a smooth surface, but the backfill surface is having a certain inclination. So this is a case where passive case which is shown, the wall position is initially here and the movement of the wall is towards the backfill. Then what will happen is that there is a wall movement. This is the wall position which is shown after pushing adequately inside to create a passive state of plastic equilibrium. Then at point of plastic state of equilibrium, a rhombic element is shown here. So in this case, these stresses can no longer be called as principal stresses because these surfaces are not horizontal, so they carry some shear stresses. So but these particular stresses what you are showing, this is sigma z at a depth z along this z is measured here as shown here, and sigma a is the active earth pressure, and sigma z at a depth z, and sigma z is vertical stress here. So this is a typical rhombing element in case of active case, and this is a case in the passive case where you have got sigma p as the passive earth pressure and sigma z is the vertical stress. So as these stresses are not normal to their respective planes, they are not principal planes. That has to be noted. Now in this case, assumptions involved in this case in extending this theory to this particular case, this existence of the conjugate relationship between the vertical pressures and lateral pressures on vertical planes within the soil adjacent to a retaining wall. So existence of conjugate relationship between the vertical pressures and lateral pressures on the vertical planes within the soil adjacent to a retaining wall. That means that these are the vertical planes which are there. So what is being shown is that existence of conjugate relationship between the vertical pressures and lateral pressures on vertical planes within the soil adjacent to a retaining wall. The effect of wall friction and friction wall the soil is neglected. So with this assumption, what it means is that the effect of wall friction or friction between the wall and the soil is neglected. So with this assumption, the Rankine action theory is extended to calculate the earth pressures for a case. Now what we need to do is that to extend this theory, sloping of soil surface with smooth vertical retaining wall. So consider this particular horizontal length is actually having a unit length. Now weight of the column soil above the horizontal width is gamma z, that is the at depth z in the as you shown in that rhombic element. Area of the parallelogram is z into 1, that is the z is the depth and 1 is that unit width. Then volume of the parallelepiped is z is equal to 1 into 1. The area of the face is 1 by cos beta into 1. So sigma on the face of the element parallel to the slope surface is gamma z by 1 by cos beta into 1, which actually gets sigma z that is gamma z cos beta, that is the sigma v on the face of the element parallel to the slope surface, that is on that inclined, which is parallel to the slope surface means which is having an inclination beta. With that sigma a is equal to, now we can obtain Ka gamma z cos beta. Suppose if cos beta is equal to 0, then it actually changes to sigma a is equal to Ka gamma z. With some inclination beta, what we get is sigma a is equal to Ka gamma z. In case if it is for passive case, then sigma p is equal to Kp gamma z cos beta. Now by further simplifications and deliberations, we can actually obtain coefficient of active earth pressure for this case where the fill surface is not horizontal, is inclined with having a beta with horizontal. For a smooth vertical retaining wall with vertical face, we can actually obtain Ka is equal to cos beta minus root over cos square beta minus cos square phi divided by cos beta plus root over cos square beta minus cos square pi, where if you set beta is equal to 0, it actually changes to Ka is equal to 1 minus sin phi by 1 plus sin phi. This is a typical ideal retaining wall case where smooth interface and backfill surface is horizontal. So similarly, for passive coefficient of earth pressure can be obtained. Kp is equal to cos beta plus root over cos square beta minus cos square phi. Cos beta minus cos square beta minus cos square phi. With that, what will happen is that Kp, coefficient of passive earth pressure, can be obtained. So when you substitute beta is equal to 0, Kp also changes out to 1 plus sin phi to 1 minus sin phi. When beta is greater than phi is not possible, because the phi is suppose if it is more than its angle of repose, then there is which is not possible. When beta is equal to phi, Ka is equal to Kp is equal to 1, which is incompatible with the real soil behavior. So when with the beta is equal to phi, Ka is equal to it actually these coefficients change to Ka is equal to Kp is equal to 1, which is incompatible with the real soil behavior. Suppose now you have got a case where there is a vertical wall and there is say vertical wall of height 8 meters, and there is a slope inclination that is of the fill behind the wall is say 20 degrees, that is beta is equal to 20 degrees, and soil is having a unit weight gamma. Then you can determine the active thrust like this. Suppose if you have got a wall of 8 meters, then if the beta is equal to say 20 degrees, then now the condition is that wall is smooth, that is the Rakhine case. So we cannot use 1 minus sin phi by 1 plus sin phi, but we need to use this particular coefficient of active earth pressure, say Ka is equal to for the sloping soil surface, but still Rankine case. With that, we can by substituting for beta is equal to 20 degrees and say phi is equal to some slope inclination, say 40 degrees. With that, with phi is equal to angle of internal friction, with say for example for 40 degrees, then we will be able to get Ka is equal to cos beta minus root over cos square beta cos square beta minus cos square phi by cos beta plus root over cos square beta minus cos square phi. With that, we will be able to get the coefficient of active earth pressure for this case. So by substituting in sigma A is equal to Ka gamma z cos beta, we will be able to get z is equal to h, we will get the earth pressure ordinate here parallel to the slope surface of the fill, then Ka gamma h cos beta. The resultant thrust is actually determined by Pa, that is which is indicated here. So this is how that one of the case which actually can be extended like the theory of Rankine's theory, ideal Rankine wall case to a case where sloping soil surface, and in this case what you need to do is that use appropriate expressions for coefficients of active earth pressure and passive earth pressure, and determine those coefficients of active earth pressure and passive earth pressure correctly, and then use the expression for sigma z is equal to Ka gamma z cos beta, where beta is the slope inclination of a backfill surface. With that, we will be able to get the earth pressure ordinate or equation for earth pressure. So from there, we will be able to calculate the active earth pressure thrust due to soil, but we having an inclined backfill surface. Suppose we have say a retaining wall which is smooth but inclined retaining wall. Suppose if you initially, let us consider, suppose you have got a wall face all the time we are actually assuming vertical and smooth, and backfill surface is horizontal. Suppose you have got a wall, say typical masonry wall, say assume that it is smooth. In such situation the earth pressure is resultant of the weight of the soil in that wedge portion and the lateral thrust exerted by the soil. So in this case, suppose if you are having a inclined wall face but a smooth interface but with a backfill surface inclined, in that case how we need to determine is that we need to determine first the weight of this wedge, which is W, and then the resultant active thrust along this face. Now this face which actually is the frictionless interface, and with that what will happen is that you will be able to get the Pa. The resultant of W and Pa, which actually is somewhere here, that is nothing but the resultant active thrust which is need to be considered in designing a wall which is having a inclined slope face and having a smooth interface along the behind the wall. So, in these lectures what we try to in this lecture what we try to understand is that how the Rankine's theory can be used for computing earth pressures, and we also discussed the problems like a simple homogeneous soil deposit and cases like when we have got a partially submerged soil behind the retaining wall, and what will be the influence of raising groundwater table on the lateral earth pressure, especially for a active case. And then we try to also discuss the extension of this problem for stratified soil deposits. Then what we need to do is to consider the equation sigma A is equal to Ka gamma z minus 2c root Ka plus Ka q for active case. In case of passive case, sigma P is equal to Kp gamma z plus 2c root Kp plus Kpq in case of a passive case, and follow the case like when you got a interface, say two soils are separated by say interface AA, then consider the soil properties for that particular depth above that interface and below that interface, and try to get the pressure diagram for the case. So, when you wanted to calculate say for a particular, say for a cantilever sheet pile wall, then you need to calculate the net earth pressures from the active side and passive side, and those things have to be considered in the design for as a net earth pressure diagrams. So, and also further we extended this theory for determining say a case like having inclined wall face, that is, but it is smooth in nature but having horizontal surface. Then in that case what you need to do is that you need to determine the weight of the soil in that triangular portion, wedge portion, and then active earth pressure due to the horizontal surface, the conventional one. So, that is the resultant. For example, if you have got a wall which is having a vertical face with inclined surface, then we have actually discussed about the coefficient of active earth pressure and passive earth pressure with the new expressions. And but when the beta is equal to 0, they again change over to Ka is equal to 1 minus sin phi by 1 plus sin phi, and Kp is equal to 1 plus sin phi by 1 minus sin phi for a passive case. And we use these things to calculate the active earth pressure thrust and passive earth pressure thrust. In the next lecture, we will be introducing the Coulomb's theory of earth pressure, and then graphical methods for determining the earth pressure, and thereafter we will be discussing examples relevant to Coulomb's and Kalman's methods.